Okay, well, everyone, thanks for coming. This is our second event in the series. We're talking about winds and outflows as broadly as you can imagine. So today, I think we're going to hear a lot about how accretion and inflow often comes with the reverse and outflows. And so we're delighted to have Erin today. She's a Hubble Fellow and Joint Space Initiative Fellow at the University of Maryland right now. You did your PhD in Cambridge in 2015. And today we're going to hear some about Super-Eddington accretion onto supermassive black holes in the local universe. And I think Erin recently has really been transforming our understanding of the physics of accretion in tidal disruption events where stars get disrupted by black holes. So we're delighted to have her today. And let me just remind you of our sort of format. So we're going to have Erin talk for 40 minutes. We'll have pizza. And then so everyone can get up, get pizza, and then come back, and we'll have question and answer and discussion from there. So so we'll take a 5-minute break, get food, and then I'll come back together. So thank you so much.
Great. Thanks, Morgan. Thanks for that nice introduction. All right, so it's wonderful to be here at Harvard. I've had a great trip over the past 2 days. I'm going to be telling you guys about Super-Eddington accretion in the local universe, talking about some of the work that I've done on tidal disruption events, but also about ultraluminous X-ray sources. So just to start out, as a kind of broad motivation for why we're studying Super-Eddington accretion, why we care about it in the first place, we have observations like this one from a recent paper in Nature just a few months ago, an 800 million solar mass black hole in a significantly neutral universe at a redshift of 7.5. So we're seeing now that we can look back to the very early universe, when the universe was just 5% of its current age, 690 million years old, we're seeing these very large, some of the biggest supermassive black holes that we know of in the universe. And it begs the question, how do these black holes grow? And I kind of plucked this slide from a public talk that I gave recently and to a high school. And one of the students immediately rose their hand and said, what do you mean growing a black hole quickly in 690 million years? What does that mean? And of course, if you don't have an understanding of the Eddington limit, this theoretical limit for how fast you can grow a black hole before radiation pressure dominates outwards, then that is a fair question. 690 million years old, does this sound like a long time? But the reason that it's important to understand this, and the reason that it's a big question, is because if you start out with a black hole seed, basically at growing in a kind of normal way through the collapse of a massive star, you can get if you use population 3 stars, you can get a 200 solar mass black hole as your seed in the very early universe. And so in order to grow that small seed to an 800 million solar mass black hole at a redshift of 7.5, you need to have these bursts of Super-Eddington accretion. And of course, you could start with a bigger black hole seed, but for this talk, the motivation is, well, could we start with these smaller black hole seeds and grow at Super-Eddington rates, and what would that look like? So this has motivated a lot of theoretical work in recent years, nice MHD simulations of Super-Eddington flows. This is just showing 2 from people that you know of, I'm sure. And you can see in these 2 different examples of Super-Eddington flows, the overall radiative efficiencies is kind of still debated. Is there a pointer here? That's okay. The overall radiative efficiency is still debated, but the kind of general picture is the same. That you no longer have a thin accretion flow. Oh, thank you very much. you won't have a thin accretion disk in these systems. There's a lot of radiation pressure. There's so much radiation pressure that you see these outflows, these strong outflows due to radiation force. So you'll have material flowing inwards at Super-Eddington rates, and material Compton thick winds being launched here. Often you'll have this evacuated funnel where a lot of the radiation can escape. And this is a general picture that we see from a lot of these MHD simulations coming out. So the question is, me as an observer, do we see evidence for this in observations? And so we can't probe those black hole seeds at a redshift of 7.5, or those supermassive black holes at the early universe. We can't really probe those in great detail, and so what this talk is about is looking for local analogs to study the physics of Super-Eddington accretion in detail. And so in this talk, I'm going to be giving an overview of observations of ultraluminous X-ray sources, and then at the end I'll talk about some of the work that I've been doing on tidal disruption events. So ultraluminous X-ray sources, to start, they are defined as off-nuclear X-ray sources with X-ray luminosities of 10 to the 39 ergs per second or greater. And that's 10 times the Eddington luminosity for a 10 solar mass black hole. So that's an example of one of these ULXs in a nearby galaxy. But of course, the question is, we basically just define these things by their luminosity. And then the bigger question is, well, what is the mass of these things? Are they really 10 times the Eddington limit? Are they 10 solar mass black holes? Or are they intermediate mass black holes? And this is kind of, when these ULXs were first discovered, the idea of either having Super-Eddington accretion on a 10 solar mass black hole or having IMBHs, either one of those possibilities is quite exciting, because we know of two populations of black holes. Of course, LIGO is kind of probing deeper into this higher mass range, but we know that there are these stellar mass black holes, not much more than 30 or 60 solar masses. And we also know of a population of supermassive black holes from 10 to the 6, maybe 10 to the 5 to 10 to the 10 solar masses. And when we look at these populations of accreting sub-Eddington accreting black holes, they show very similar X-ray properties. This is an example of a black hole binary observed with NuSTAR. Even in the high soft state, the thermal dominated state of these black hole binaries, you get this non-thermal tail of hard X-ray emission that extends up to beyond 100 keV. And again, here's an example of a supermassive black hole. This is MCG6 minus, whatever, by Andrea Marinucci. And again, you're seeing this non-thermal X-ray emission extending up to 100 keV. So these are what we know of as sub-Eddington. This is kind of like ubiquitous in sub-Eddington accretion onto black holes. But NuSTAR has discovered that ultraluminous X-ray sources, or at least many of these ultraluminous X-ray sources, don't look like the sub-Eddington black hole binaries or AGN that we know of in the local universe. And this is showing an example of two of these sources. They show these very soft spectra that cut off. Really, there's very little emission above 20 keV, and they can say that pretty definitively now in a lot of these sources. That you see this, and it's often modeled as these, two components. Some people will say there's this disk black body component and maybe a non-thermal tail with a cutoff at high energies, but you never see this non-thermal component extending up, or in very few ULXs. Do you see a non-thermal component extending up to 100 keV? So this kind of was one of these arguments that, well, Super-Eddington accretion may be this corona that's producing this non-thermal emission, maybe it's cooled very efficiently in these Super-Eddington accretors, and that's why you don't see this hard X-ray tail. So it's not definitive proof that these cannot be IMBHs, but you could make the argument that if there are accreting, sub-Eddington accreting IMBHs, why wouldn't they look the same as the stellar mass black holes that we know of and the AGN that we know of as well? So that was an important thing coming out of NuSTAR. So there have been lots of observations of ultraluminous X-ray sources in the X-ray band, and this is kind of a compilation that Chiro Pinto put together, but it was really kind of first discussed by Jeanette Gladstone in 2009, that you see there are kind of states of ULXs, and when you look at different ULX systems, they kind of, some of them show this very kind of harder spectrum. Very, again, not much emission above 20 keV, but some show this harder emission. Some are extremely soft like this. And some even transition from a kind of very ultra soft state to a slightly harder state over time. You can see that in the cyan points there. And if you put this together, you can kind of think of a unified picture. In this picture of a Super-Eddington accretor, you could think of a unified picture like this, where the harder ULXs that you're seeing here are the ones that are observed more face on, so you're seeing the hottest bit of the accretion flow. And these ultra-soft sources are seen at more edge-on, where you're probing the photosphere at much larger radii, and so you see lower temperature emission. And this is kind of a tempting picture, of course, to put everything together. And your colleague Ramesh Narayan has taken taken the results of MHD simulations and done radiative transfer calculations of Super-Eddington accretion flows for a 10 solar mass black hole accreting at Super-Eddington rates, and finds that you can reproduce a similar kind of evolution to explain the observations that we see, that as you go to lower and lower inclinations, you're probing more of this hot inner flow and getting this harder X-ray emission.
Is there any data on variability that indicates how close the emission is?
So that's a really excellent question. And so they don't vary an incredible amount. There's not a lot of rapid variability. There have been claims of QPOs in one of these, or maybe a few of these sources. And if you believe those QPOs, and if you think that they are associated with the high-frequency QPOs, or they're equivalent to the same mechanism producing the high-frequency QPOs in black hole binaries, if you scale those frequencies, then you get a mass of an IMBH. But we don't really know what QPOs are, so take that with a grain of salt. But they don't vary an incredible amount on fast time scales. So yeah,
I'm going to ask about the variability on longer time scales, because I know we actually studied this one in M101, the ultraluminous soft source there, and some others. And the thing is that they don't stay soft. They change around, and it depends on the luminosity. Sometimes they have hard tails, sometimes they don't. Sometimes they're not soft at all. And so in this picture, where we're trying to relate it to the geometry, how does that work? It looks like you're kind of doing that by putting these two together.
Right. So I mean, especially, you take a case like you're describing, where it does have variability. Sometimes you see it as a harder thing, and sometimes as a softer thing. So that really must be, obviously can't be an inclination effect alone. So there must be some other eigenvector, some other, it's mass accretion rate, for instance. If you decrease the mass accretion rate, the disk isn't as puffy, and maybe you're able to probe further. You're able to see more of the hotter parts of the accretion flow and it changes the
Similar to transitions in ordinary
Yeah.
black holes, stellar mass black holes.
right.
But the other interesting thing is that in the soft state, if you ask yourself that this would be if the inner disk corresponds to the last stable orbit, there are cases in which you get something which again would be comparable to an IMBH. It's not universal, but it's another argument for masses. But I don't think we can trust that argument because we don't really know what's determining the radius of that.
Exactly.
disk.
Exactly.
Yeah.
That's my feeling as well. Yeah. Yeah. Good. Yeah. If there are questions throughout, please, we don't have to wait for all those discussion at the end. Yeah. So this picture of ultraluminous X-ray sources as Super-Eddington accretors is kind of coming together nicely in this, unified picture of Super-Eddington flows. And one of the other nice observations that kind of go along with this idea of Super-Eddington accretion was the discovery of ultrafast outflows in ULXs. These have been seen now in a handful of ULXs. This is work by Ciro Pinto, and you can see that there are absorption features in this spectrum here, and they are blue shifted by 0.2 C. Several of these atomic features blue shifted by 0.2 C, and they estimate that 50% of the total energy budget is lost in this wind. So again, you don't require that these winds need to be launched through radiation force, but it is an expectation, if you have a Super-Eddington accretor, that there will be radiatively driven winds at these fast velocities. And this is just kind of an advertisement for where we hope that we're going. Just a short, this is what the same observation, what XARM Resolve, the Hitomi recovery mission will see in 250 kiloseconds. So we'll really very nicely see these absorption features in very faint sources, I should add. And then with Athena, we could do a similar thing, a similar quality observation in 10 kiloseconds. So we're really excited, looking forward to those two missions. So then, now we have observations. We've seen these ultraluminous X-ray sources. There's kind of a growing consensus in the community that these are Super-Eddington accretion onto stellar mass objects. But recently, there's been a kind of wrinkle in that idea. And that came with the serendipitous discovery of the fact that some ultraluminous X-ray sources are in fact pulsars. And this was another observation from the NuSTAR Observatory. It was kind of one of these beautiful things that came about. NuSTAR never was intending to look at this ULX because there are actually two ULXs in M82, and they can't be resolved by NuSTAR, and so NuSTAR was not going to spend a lot of observing time looking at these ULXs. But then there was a supernova that went off in M82, and so they devoted a lot of time to observe this galaxy, and they kind of got these observations for free. And what they found when they looked at those, Matteo Bacchetti looked at those observations, he found that M82X2 had a pulsation at around 1 second, a 1 second pulsation, very coherent pulsation. Now they've gone back and they've looked, a few authors have gone back through the XMM archive searching for pulsations in ultraluminous X-ray sources, and now there have been 3 confirmed pulsations, and you see this is an example from Israel's 2016 paper of a period of 0.42 seconds, so very consistent with what they see in just regular pulsating neutron star systems, and the pulse profile is very sinusoidal in all of these objects. So the interesting thing is that when you look at the spectra of all of these sources had been kind of thought of as accreting black holes. That was kind of the paradigm that people had been thinking for them, because they show spectra that look very similar to a lot of the ULXs that we know of, that they show this very soft, double humped structure and very little emission above 10 keV. So this is kind of important for two reasons. First of all, now that we know that this is a neutron star, we know that this thing is 500 times the Eddington limit for a neutron star system. So we know that super-Eddington accretion onto compact objects is happening. That's now confirmed. But now the question is, what is the compact object? And because these spectra don't look kind of unusual, the question is, we know that neutron stars are 10 to 50 times more common than black holes. Are all ULXs pulsars now? So this is a question that I think is still the community is still grappling with. It seems like, do all ULXs have to be the same? Maybe some are black holes and some are pulsars. They know that not all ULXs show pulsations, so could there be a wide range of origins of these things? But I think we still need to understand why their spectra look the way that they do. So that's kind of what I wanted to present on ULXs. And now we'll talk about tidal disruption events where a star gets too close to a supermassive black hole. This is the, I feel obliged to show this schematic from Martin Rees's paper. A star comes in, there's a black hole at the center of a normal galaxy. And at this tidal radius, the strong tidal forces from the black hole become stronger than the self-gravity of this star, and it gets ripped apart. Some of that material will continue on its original parabolic orbit, but some of that material will be bound and will fall back towards the black hole. And this is now the fallback rate, showing the fallback rate as a function of time by Evans and Kochanek. And it shows there's this very distinctive fallback rate that you have for a 10 to the 6 solar mass black hole, you'll have a rise time as the material falls back. And then at its peak, this fallback rate can be 2 orders of magnitude higher than the Eddington limit. And then over time, it will decay as this characteristic t to the minus 5/3 decay. So the fact that this fallback rate is potentially 2 orders of magnitude above the Eddington limit is very exciting. And the question is, does the material is falling back towards the black hole at these high rates, but how does it lose that angular momentum, that orbital energy, and accrete? And does that accretion onto the black hole happen at rates, at super-Eddington rates as well? So there are a couple of exciting reasons why people are getting into the study of tidal disruption events, and I hope to convince you that they are very exciting. First of all, as probes of super-Eddington accretion, how fast can you grow a black hole? TDEs also provide a way to probe a population of quiescent black holes. You take a normal galaxy and you basically give it an impulse of accretion, and you can watch that happening in real time. And so it's kind of a way to probe, potentially probe the distribution of black hole spin in quiescent galaxies, not just in AGN. If you disrupt a white dwarf, you could disrupt a white dwarf by an IMBH. So maybe it's a way of finding this potentially missing population of IMBHs. And then again, and lastly, as I alluded to, it's a kind of potentially clean environment for testing accretion. You give it this impulse of accretion. You can watch disks and jets and coronae form in real time, and you can watch that transition happen potentially from a super-Eddington rate to a sub-Eddington rate, all in the same black hole. So there's no, confusion as to the mass. But you can watch this accretion state change on timescales of months to years. But of course, the question is, we talked about the material falling back towards the black hole at these Super-Eddington rates. How does it lose its orbital energy? And this is a question. I've been to a couple of TDE conferences in the past year, and it's like this is one of the big questions that people are still grappling with. And in order for this material, so like if you take an example like this. If you have ballistic accretion, all of that material, the falling back towards the black hole, will accrete onto the black hole. You have your light curve the mass accretion rate will follow the fallback rate, and you'll get these Super-Eddington mass accretion rates like this. But if you have inefficient circularization and you can't accrete the material very efficiently, then you may see something like this that doesn't reach the high Eddington accretion rates and doesn't follow this to the minus 5/3 decay. And so the question is, how does this, how efficient is this circularization process? And the answer may come with stream-stream collisions. So you have material that is bound to the black hole, and it's a stream of stellar debris. Eventually, that could intersect with the remaining stellar debris, and it can lose some of its angular momentum through this process. Now, if this stream-stream collision happens very far from the black hole, then it'll take a long time for this material to eventually accrete onto the black hole. But if it happens, if these stream-stream collisions can happen very close to the black hole, then it circularizes extremely quickly, and you can accrete at these high Eddington rates. And so the difference between these two scenarios could be due to how close the stellar debris gets to the black hole. If the penetration factor is very high and the stellar debris gets close to the black hole, there will be a lot of apsidal precession, and you can self-intersect your debris stream at very small radii and accrete very quickly. And then your mass accretion rate onto the black hole will match this fallback rate quickly. Yeah. So this is just showing a nice simulation of this by Clement Bonnereau. This is a hydro simulation of this debris stream, the bound debris stream for the inefficient circularization case. The penetration factor is lower in this case, so it's not getting very close to the black hole. There's not a lot of apsidal precession, and so it takes a long time for that accretion process to circularize and accrete slower. Whereas in the efficient circularization, where you're getting very close to the black hole on your first passage, you see that circularization happens very quickly, and you can accrete at these Super-Eddington rates. And there's lots of debate still in the community. Yeah. So the amazing thing is that we actually observe these TDEs. I think that that's so cool that we're watching in real time black holes getting ripped apart, or stars getting ripped apart by black holes. They were first observed in the X-rays with the ROSAT all-sky monitor in the mid-90s, and Stephanie Camosa has been a real pioneer in those efforts. And in the soft X-rays, we see a lot of thermal emission, like a 10 to the 5, 10 to the 6 Kelvin black body emission, which is around the ISCO for a 10 to the 6 solar mass black hole. So it seems like in these soft X-ray ones, maybe you have this very efficient circularization process, and you have this accretion happening, at these high rates. They're also found, and mostly nowadays with these large optical surveys, they're found in real time, or soon after the outburst in optical. And this is a nice, probably one of the best examples of a TDE found by Suvi Ghazari. And when you look at these optically selected tidal disruption events, they show a characteristic black body temperature of 10 to the 4 Kelvin. And so that's much cooler than you'd expect. That's about 1,000 RG for a 10 to the 6 solar mass black hole. So it may be that we're seeing two kinds of processes happening here. That maybe the emission that we're seeing in these optical TDEs are from inefficient circularization, where you have emission coming from these streams colliding at large radii. Or maybe you do have efficient circularization happening, but there's some reprocessing in layer in the optical. But you definitely, there seems to be that the optical is showing these cooler thermal spectra. And so it's still a question exactly, especially in the case of these optically emitting TDEs, where exactly the emission is coming from. But the X-rays, I think, seem to be a cleaner signature of Super-Eddington accretion. And so really that's what I'm going to be focusing on for the remainder of this talk. So yeah, I mentioned that there are kind of these different observed types of tidal disruption events, these optically selected ones where the emission could be from the stream-stream collision or from reprocessing in a photosphere at larger radii. And then you see these soft X-ray detected tidal disruption events, and these look like good candidates. They have high luminosity to be Super-Eddington accretion from emission from a Super-Eddington disk. And lastly, we have 3 observations of tidal disruption events found in hard X-rays with the Swift BAT telescope. And these seem to be, they're also accompanied by radio emission, so it seems like you're seeing a relativistic jet, and could be, so we're watching relativistic jets form in real time. And so I'll be focusing on these X-ray emitting TDEs for the remainder of the talk, because this is a kind of about Super-Eddington accretion. So first, Swift J1644. This is one of the most well-known TDEs. It was one of these hard X-ray emission TDEs found with the Swift BAT. This is the light curve in the X-rays. This is the X-ray flux as a function of time. And these gray points that you're seeing here are the Swift BAT sources. They did a really nice high cadence monitoring. But it was an extreme event like nobody had ever seen before. So, of course, all of the other X-ray telescopes slewed to this event. And so there are Swift observations and a bunch there are Suzaku observations at early times and a bunch of XMM-Newton observations as well. So I'm going to be focusing on these first 2 observations and specifically this first XMM observation. So when I looked at this XMM observation from early times, I got really excited, because you can see that even on short time scales, this is a 20 kilosecond observation with XMM, even on short time scales, you're seeing very rapid variability. And so you can do a lot with these kinds of observations where you have a lot of variability. And the reason that I got excited is because we've been using this rapid variability in AGN to probe the inner accretion flow around these AGN. And in particular, we've been measuring light echoes in sub-Eddington AGN that kind of map out the inner accretion flow within tens of gravitational radii of the black hole. And so this is just an example of kind of what we're seeing in sub-Eddington AGN. This is, again, observations taken with NuSTAR. You see, when you look at the spectrum and you divide out some model of the continuum in these sub-Eddington AGN, you see this broad iron K alpha line and this Compton scattering hump. And these are thought to be reprocessing features off of the accretion disk, the inner accretion disk. And when you take that same data and you look at the corresponding lags as a function of energy, you see that there's a lag associated with this broad iron K alpha line and this Compton scattering hump. And so this lag that we're seeing, we associate this with an additional light travel time that those reprocessed photons have had to take. And so it's a kind of new way of probing this inner accretion flow in sub-Eddington AGN that are indicating that we're seeing reprocessing at small radii. And so now that we have these observations of a tidal disruption event that shows this rapid variability, we can do a similar kind of analysis, and this is what the results are. It was much better than I actually anticipated at all. What was amazing was that we found an iron K alpha reverberation lag in this object. And this is it right here. You can see it also just by eye in the light curve, which is kind of unusual for these things. That if you look at the light curve of the continuum-dominated band and the light curve of where we see this line, you can see on average the red, the line, is lagging behind the continuum. And again, when we went back and did a clear cleaning of the time-integrated energy spectrum, we found at the same energy where we see this peak in the lags, we're seeing a small equivalent width feature at the same energy, at 8 keV. So in the case of sub-Eddington AGN, we see this, the rest frame iron line is at 6.4 to 7 keV, but we're clearly seeing that this line is very heavily blue shifted in this tidal disruption event. And in addition to that, this is a source where there was also a radio detection. I didn't mention this before, and I should have, that the isotropic X-ray luminosity for this thing was 10 to the 4 times Eddington. And so 10 to the 4 is kind of huge. So it seems like it's something that's beamed towards us. And then you can get down to kind of more reasonable Eddington luminosities. So in this case of a system that seems like we're kind of face on to it, we're seeing a highly blue shifted iron K alpha line, and we interpret this as reprocessing off of an outflow at 0.3 to I should say 0.5 C, depending on what you assume as the opening angle of your funnel. So this is kind of the geometry that we're suggesting, that in this hard X-ray emitting tidal disruption event, you're looking at this Super-Eddington accretion flow kind of face on here. Again, you're seeing these fast radiatively driven outflows, this Compton-thick outflow. And if you have some impulse of emission from X-ray emission that's kind of some part of which is emitting more isotropically, you can have reprocessing off of this outflowing Compton-thick wind and get the blue shifted iron K emission there. So that was kind of an exciting discovery. We were seeing winds that are that make sense in this paradigm of Super-Eddington accretion, and so I kind of got excited about looking at more TDEs, and so I looked at some data from Assassin 14Li. This is a tidal disruption event that was discovered by the Assassin survey in 2014, and it is one of the most nearby tidal disruption events ever discovered. And it emitted in the optical and in the UV, in the soft X-rays. Kate Alexander did a really nice job looking at the radio. There's radio detection as well. It was just a really spectacular event. And you can see this is the long-term light curve as seen by Swift. And this is the broadband SED. And you can see there's UV and soft X-ray emission here. And we're seeing this 10 to the 5 Kelvin black body emission with very little emission above 1 keV. So again, kind of similar, perhaps similar to the ultraluminous X-ray sources that don't show this non-thermal X-ray continuum out to 100 keV. In these soft X-ray TDEs, we also see no evidence for hard X-ray emission. And there were a slew of observations on this target that I wish I could go into more. Julian Krolik called this a model tidal disruption event. There were soft winds, slow winds found in the X-rays and corresponding winds seen in the UV spectra. Kate saw again this radio detection, which she interprets as an outflow of 0.3 C. And there were also IR dust echoes, so they could use those as a kind of a calorimeter to measure the bolometric luminosity of this thing. And the error bars are huge, but it's a promising technique. But when we looked at the X-ray observations of these things, again, Swift looked at this object. These are the gray points, but XMM-Newton also did some follow-up pointed observations at very early times, and then about a year later when it had significantly dropped in luminosity. And when we look at these early time observations taken within 40 days of the initial discovery, we found that when you divide out a model for this thermal 10 to the 5 Kelvin black body emission, what you see in the residuals is this feature that looks kind of like a P Cygni profile. And it's in the CCD spectra on board XMM, but also in the grating spectra as well. So it's definitely not something to do with the quality of the readout time of the CCD, because we also see it in the grating spectra. And yes, it's one feature, but the best model that we found to interpret this was through some photoionization modeling, and we think that it's the oxygen 8 absorption at a 0.2 C blue shift. So you can kind of like put these two things together now and try to create, maybe there's a unified picture for Super-Eddington accretion in tidal disruption events as well. Whereas Swift J1644, this is a source that we think is seen face on. Maybe it has a high spin or has more magnetic fields or something, because it also produces a jet. But we're seeing evidence for these fast outflows in emission off of this Compton thick accretion flow. Whereas Assassin 14Li, you're seeing only soft thermal X-ray emission. Maybe you're probing the photosphere again at larger radii, and you're seeing this wind, a slower wind in absorption in the case of Assassin 14Li. And this is congruent with a recent paper that is soon to be accepted, hopefully, by Jane Dye, where she took some MHD simulations and did radiative transfer of these, and also found that you could explain the hard X-ray, soft X-ray, and optical emitting TDEs as just simply or mostly an inclination effect. So that's a nice kind of way of tying it together, I think. One of the interesting things as well, and something that I want to go into more, is kind of probing the evolution of these accretion flows now. So one of the things is that these outflows in both Swift J1644 and in Assassin 14Li are only seen at early times. So in Swift J1644, we found reverberation in this XMM and in this Suzaku observation. And in Assassin 14Li, we can rule out at a 2.7 sigma confidence that the outflow is not in the late time observations. And so the question is, this kind of, if we are transitioning from this Super-Eddington phase at early times to a sub-Eddington phase at later times, you're no longer launching a strong wind. Maybe it makes sense that you're not seeing an outflow there. But I think it's something that's that we need to disentangle from just data quality issues. And so hopefully we'll get another bright TDE in the next year or two, and we have a long observation to probe a TDE at late times, a few months after the initial outburst, to see if we can see this evolution. I think I will skip this last thing and just go to my conclusions. I hope that I've convinced you that there's increasingly stronger evidence for Super-Eddington accretion in the local universe, and we're seeing evidence for strong winds in Super-Eddington accretors. And perhaps these both can be explained through a kind of unified picture, but there are definitely still many open questions. So, thank you.
So yeah, I think we have time for a few questions as the pizza gets set up, then we'll take a break and come back for more discussion.
So these ULXs that are interpreted as neutron stars,
Yeah.
it's very puzzling, 500 times the Eddington luminosity. What mental picture people have of these pulsating neutron stars? Because if you have so much stuff falling onto them, you won't see the pulsations very easily.
Yeah, so
what's going on there?
I guess you need some, the idea is that you have accretion through, Super-Eddington accretion through a column, and then you have radiation coming out, escaping, sideways, and that's what gives you kind of the pulsations. But
So the magnetic field needs to be strong enough so that it collimates
that's right.
the infalling material.
Yeah.
So is the infalling material on the poles or on the equator?
On the
On the
poles.
poles. And where is the emission coming from? The equator?
From this accretion column,
From the poles?
from the base of from the pole.
So somehow the radiation manages to get out, even though there is so much material falling in. I mean,
Right. So I think
very thick.
it needs somewhere to escape, and like in some of these models that it's, accretion on the column and then radiation out. So,
But
yeah.
with Super-Eddington, you can easily show that once the luminosity is above Eddington, the mass accretion rate is about, the optical depth for Thomson scattering is certainly much larger than 1. It just comes from the equations. So the fact that there are 500 Eddington means that the optical depth for Thomson scattering is 500 or something. And then how does the radiation come from the pole out? Did anyone try to model it?
I mean, people are actively working on it, but I don't think that there is a clear picture. So maybe that's your next project.
It's not necessarily this sort of
Episodic?
smooth accretion. Well, episodic in a sense, but I mean that the geometry of it can be clumpy. And so you can have light that escapes in some regions where it's less dense, but overall you're really having Super-Eddington accretion. So our typical calculations are perhaps, we like to consider the simplest case, right? But that nature, especially, I don't know what kind of companions these have. Is that known? Is that
I'm
also
not sure.
determines how clumpy the infall is? And, what determines whether you can have accretion at this limit is really the companion. You have to have a lot of mass to give in order for something to accrete that much mass.
Yeah.
So it isn't so much how massive the object is, it's how much mass is available to go to it. So certainly, people have both been looking at the accretion and saying, well, this could be clumpy, and clumpy models may explain what we're seeing. But if you have a donor star that is a high wind object, there are all sorts of structures in these winds that are very difficult to
Yeah.
But this was not predicted ahead of time.
Oh, God,
so
no.
Clearly the theory did not have a good enough
Yeah.
imagination.
Well, then it gets even more complicated because NuSTAR went back a year later or something, and they observed this source again, and the luminosity hadn't changed, but the pulsations had turned off. So the spectral shape is very similar, but maybe it is something like clumpy accretion, but then you also have to explain the...
It's an excellent point about the pulsations not coming out. This was a puzzle for years in X-ray astronomy where we knew we had accreting neutron stars and we couldn't see the pulses. And we knew they were being spun up to null sections and we couldn't see the pulses. And now people have found them in some systems. It's very interesting. But all of the pulsations are on the order of second pulsations
Yeah.
for these. So it is clear it's a neutron star. And
Yeah.
something else.
And it's a very coherent signal, yeah.
So if you integrate the accretion rate over time, how long before you push the neutron star into the kind of superluminous velocities?
I don't know. I don't know the answer to that.
What's the Eddington limit for the Eddington accretion rate? gives you, I mean, it doubles the mass of the object.
I think about a million years.
No, but this is 500 Eddington, so it should be 500 times shorter than 4 times 10 to the 7 years. So 500 times shorter means 10 to the 5 years. So the object would double its mass in 10 to the 5 years.
Mm.
Well, except that it's not going to keep the mass, right? I mean, it's sending a lot. We don't know what fraction of the mass is actually being sent out.
Right.
So it's hard to know exactly what fraction is being retained.
That's a good point.
No, the radiation comes from material hitting the surface and releasing gravitational binding energy. So we can actually tell exactly how much mass is impinging on the surface. Unlike a black hole where the accretion efficiency is not, I mean the radiating efficiency is not known, here it's just 10%. You radiate 10% of the mass falling on the surface.
I was wondering if you can do something.
So from the luminosity you know the accretion rate. Yeah.
Mm.
Can I ask a question sort of related about the P Cygni profiles,
Mhm.
the blue shift emission? So is the line width similar to its blue shift always, or is it not, like, how does that all
So in this
play out?
source, in this observation that we have, the width is also huge, and it's a similar velocity to the blue shift that we
Okay.
measure.
What does that tell you something about the geometry? What is that?
Yeah, I mean, I guess this is, something that is, well, so, yeah, it will tell you something about the geometry. In addition to the width of the absorber, there's also slight evidence for the emission coming from like the rest of the material not along your line of sight.
Okay.
And in this object, like the amount of emission that you, I should say that this is like, again, another like 2.5 sigma result.
Mm-hmm.
But the amount of emission that you require suggests that it can't be something like spherical, that it needs to be something that's more of like an equatorial wind. But again, I don't want to emphasize that too strongly.
For one more second.
Yeah.
Very interesting.
Yeah.
So it seems like there's going to be an increasing kind of menagerie aspect to TDEs as more get discovered, and I'm sure there'll be all kinds of different phenomena and things that are hard to explain. As an observer, I wonder where do you think the real fire hose of TDEs will come from? Will it be like LSST, or will it be E Rosita, or something else?
Yeah. So, well, in the very near future, ZTF and also Assassin with their upgrades, they say that they should be seeing, ZTF says they should see 30 TDEs a year. And they start taking their science run like now. So we should be seeing that very soon. LSST says that they should see the rates for that are like 1,000 TDEs a year. So I think we need to really start thinking. I mean, we're not going to follow up 1,000 TDEs a year. So I think we need to think more about exactly which ones to go after. In the X-rays, so I am an advocate for studying the X-ray emission, and I think that we can learn the picture seems a little clearer in the X-rays, and so eRosita, like ROSAT, will do an all-sky monitor at the beginning of its mission, and so they hope to see 1,000 TDEs a year as well. Or, I think Kate would say that the rates are a little bit lower based on that kind of order, but they won't follow. They come back to the same place in the sky every 6 months, so you're not going to follow them up in real time. So what I want to see now is a sensitive, wide-angle, soft X-ray, all-sky, wide field of view, all-sky monitor, so we can really find these things in real time. So for LSST, I think one of the ways that we will be able to best follow up TDEs is also like getting coincident detections with X-rays.
And is the cadence high enough with LSST to track?
So LSST, I think they're talking about like a 3-day, 1-week cadence, and so for these are slow transients, so we don't really need to do much better than that. For other things,
Is the picture clearer in X-rays because there are fewer photons?
Better.
no, better photons. Yeah. Okay, is it pizza time? Okay, sorry. I thought you were asking a question, but yeah.
Yeah, okay, let's take a little break for get pizza and then we can come back and have pizza.
Yeah, great.
That's great.
Thank you.
Are they sometimes observed at X-ray as well?
So yeah,
It's clear the Russian side is clear.
yes, some of them are, some of them.
Can I give you a slice of something? Do you have a preference? I just don't want it to be gone by the time you.
Well, we can go have a pizza together.
Okay, yeah.
Oh, the lines the other way.
You're allowed to skip it though.
That's right. You can
That's kind of clear what happens with the gravitational wave.
and also at higher temperature.
Yeah, but in the first
Yeah, no, exactly. That's how it goes. Okay, let's come back to the group. I know there's lots of interesting questions. You can sit down, yeah. We have the room for another 10 minutes or something, so we can continue the conversation. Oh, maybe. I'll be right back.
Okay.
So Roseanne, maybe you can just ask your question, or pick up where you were with the group.
Oh, well, I guess it's interesting for everybody. You answered the question already, but it really had to do with the connection between some of these different systems. So the optically selected ones, you're seeing polar emission, so 10 to the 4th Kelvin, whereas for the X-ray emission, from these very nice soft ones, you're seeing something like 10 to the 6th. So the question was, are these really perhaps just different parts of the same system? And optical is sensitive to one and X-rays to the other. So Erin was giving a very nice discussion about that goes even beyond that.
Right, and there's kind of a question. Oh, thank you. There's a question in the field that a lot of these things are being found in these optical surveys now, but they don't all show X-ray emission at early times, and that could be that we haven't probed deep enough or what. But it seems them do show corresponding X-ray emission, and some of them don't show X-ray emission. And so the question is, like, is it part of the same system that you're seeing this this efficiently circularized super-Eddington accretion flow, where the optical emission is from larger radii, from photosphere at larger radii, maybe due to some X-ray reprocessing? You see lines from X-ray reprocessing, but you don't see the X-ray emission because it's masked by this shroud of gas. Or could it be that the optical selected TDEs that you don't find X-ray emission with could be just a different emission mechanism altogether, that it could be from these stream, the emissions coming from the stream collisions, and you don't get you don't produce a lot of high energy photons from that. So I think it's still like, Kate and I have been to a few TDEs in Morgan as well, to these conferences, and there's a lot of debate.
Yeah, I'd say from the radio side, there's clear evidence that there's a wide range of jet powers that are produced by TDEs. So if you have an on-axis event like Swift J1644, you're obviously going to see bright radio emission. If you had an off-axis relativistic jet, you wouldn't expect to see radio emission at early times when it's being away from you. But eventually the jet's going to decelerate, so you should see similar radio emission at late times, no matter what your initial viewing angle was. But we have some pretty deep radio limits that we've built up in both early and late time scales for a handful of events now. So a jet that's as powerful as the jet in the Swift event is ruled out for, I would even go so far as to say, a majority of TDEs in literature. Most of these are optically selective TDEs. So, yeah, although the outflow for 14 Li is, yeah, I mean, that one's a little more complicated because there's residual radio emission from the host galaxy, but the emission is at such a low level that even if there was a jet as powerful as the Swift jet, then we don't see any evidence for that in radio. And that one's one of the better, 14 Li and Swift event are definitely the two best monitored TDEs at all wavelengths, including radio. So, I mean, that's not to say it didn't produce a jet, but the jet would have had to be a lot weaker. So that's interesting too.
If you wanted to put this all in a unified picture where all of the optical perspective TDEs are from the same thing as where the X-rays are coming from a disk and the radio. So there needs to be something else, is what you're saying, that
I was saying maybe there's a range in the accretion rates that are produced.
Yeah.
So if not all TDEs reach these very highly super-Eddington rates, maybe you would not produce a jet, or maybe you just have some kind of weaker outflow, or and there's various reasons that the fallback rate might not directly map to the actual accretion rate. Some kind of viscous delay or something, you can end up with a longer lasting event that doesn't that doesn't ever reach the same high peak accretion rate at early times. Maybe that's what's going on. Yeah, but it seems it's interesting. I think it's not purely a viewing angle effect, but I like the viewing angle idea for kind of, it's not that, it's interesting though. I think there's a range of accretion rates for it, probably.
right, like as with the ULXs, with all of these unification pictures, it's never just one.
Science going on.
So are there any radio limits are there any type of disruption events where we constrain that there can't be a 0.2 or 0.3 C outflow as part of the accretion geometry? Like,
I mean, so I would probably be talking a little bit about
Yeah.
this next week. But we have a handful of events now where we can rule out an outflow of the same luminosity as this acid 14 Li, but there aren't very many of those because, one, we didn't have a radio telescope sensitive enough to do this until about 5 years ago, and two, a lot of events are much further away than this acid 14 Li, so a lot of the early upper limits, while they could rule out a really powerful jet, they can't rule out emission from this slower component. So we're starting to, go deeper and probe this, but I'd say for maybe 2 events right now, we can rule out this one of these two events was also unusual in other ways. This is IPTF 16MNL, which is this underluminous TDE that was found by the intermediate PTF survey, and that one was very faint in the optical as well, and faded very quickly. So people, maybe it's not surprising that it's radio upper limits that are underluminous as well.
One question about the geometry. Is that, if I understood correctly, when you were talking about the Swift TDE, there's a degeneracy between the opening angle and the velocity. Is that correct? So is there a way to break that degeneracy, maybe either with, I don't know, multi-wavelength data, or if you get like more detailed line shape, or modeling or something?
So I think that the radio is tricky because it looks like the radio has like a higher lens factor
Yes, I think if you.
than the X-ray, which seems to be something more extremely limiting. So I'm not sure
Yeah.
exactly how to use the.
I mean, if you're really lucky and have a very relativistic outflow, you can maybe see a jet break in the emission. We do this for GRB jets, but I don't think anybody's seen any evidence for a jet break in a radius. Then you do have to make some assumption about the angle.
And for, like the line profile itself, unfortunately we can't go back and like make more observations of these things to get better quality data. But when you look at the line profile, it also looks like it's an asymmetric line in the lags, in the lag profile, and that suggests if the rest frame energy is 6.97 highly ionized iron, then you have a redshift of the iron line as well. And again, it's a low significance result, but the line profile is better described as an asymmetric rather than Gaussian. And so that's telling you, if you believe that, that's telling you that you're getting really you're getting some emission from deep within. I mean, what I think of when you get a redshift is that you have some kind of gravitational redshift from emission close to the black hole, and in that case, you're seeing deep into this funnel. So you have to have some way of viewing into that funnel. Maybe if you get a wider opening or whatever.
And I guess with the radio, the degeneracy is actually between like the speed of the outflow and the opening angle. So if you have an independent measure of the speed and it's very well constrained with the X-rays, maybe you could use that to find that and say something. But I don't know that the error bars are good enough, certainly on the radio side, to. But I think the fact that they're roughly consistent is really exciting to me.
That's true, yeah.
Well, maybe that's a good place to stop. Help yourself some more pizza before you head out.
Thanks for coming.
Let's thank Erin one more time.
Thank you.
I really want no idea. It's interesting. It's reading modules in general. At least for me, and I know I'm not an expert on this, but it seems as if we don't really understand the frequency of everything and why it's very, individual systems change all the time. So state to state, within a state that had a very short time scale, and then, you're looking at a larger places, different states. What we kind of do is what we're looking at TDEs. You see a system go.
So the question is set the inverse.
Right, and it's triggering. There's no fast. Yeah, okay, sorry. So it would really be cool if you were able to map some of the stages to
So most people do that's
So one of the other things
So I'm curious, what's the breakdown of the levels?
there's a hardtail.
Well, that was, I mean, that's just, we're just finding that out now.
Okay.
So-
I guess I was curious if there
No.
was, if that was taken.
We already had that. Yeah. So, where's this?
Yeah.
But thank you for all that extra.
So we did it. And it's, I was kind of nervous that it might be really lopsided. But the biggest problem is.
Right.
And they totally you know, it's top down, people don't actually apply. They get some
Yeah.
they offer training and people
Yeah, I just
so savings and we didn't have a procedure to
I see. Yeah.
there's conversations.
Yeah, but it's good that
The field is
Yeah.
great, you know, the oligarchs want to, and then, you know, good fellowships.
Yeah. Yeah, no, I'm really excited.
And so it's like so. And so this is like one of the things that was
Clearly.
it looked like it might be
It was such a pleasure to see you. Thank you so much for being here.
It's really well done. Yeah. Good. And I saw you have totally packed schedules. Yeah. Of course. That's fine. So is this fine? But thank you, and thanks for not minding that I can't say that. Yeah, sounds great. Take care.
It was really nice to meet you.
Nice to meet you as well.
Yes. Yeah.
Is our
We're going to, yeah, so, what, we're going to do is, yeah, exactly, related.
My favorite sound.
Okay, I have to run, but be careful.
And I will be.
That's what side it's 8:30,
Yeah, so if you need anything, I'll be in, my office is B216. Are you in the visitor's office? Of
I'm or not. I'm